Welcome to our last video of the semester, Chapter 33 on particle physics. This discusses some of the newer concepts in physics, and it's related to nuclear physics. So we used to think that matter was made up of only protons, neutrons, and electrons. But since then, we realized that these basic entities have substructure. I think I mentioned in a previous chapter that a neutron really has a positive and a negative charge inside it, but the net result is that it's a neutral particle. So anyhow, in order to study the substructure of matter, we've had to resort to particle accelerators, and we will discuss them in just a minute. To study these things, we've looked at projectiles that have really high speeds associated with them. Now, in nature, this happens all the time in the form of cosmic rays. The Earth is being bombarded constantly from deep space by these charged particles that whiz through with high energies. And you can detect them using cloud chambers and other things as well, but the cloud chambers are a really cool way to look at cosmic rays. But when you want to quantify things, usually you need a particle accelerator. So they're used to produce particles through artificial transmutation. So we take a particle and we slam it at a target and then look at the end result. And a lot of times these end results give us information about the substructure of the atom, and we can then take it from there. So in every case, what we do is we have a charged particle and it's moving in such a way as to increase its speed. There are two types of particle accelerators. We have linear accelerators and cyclic accelerators. Whoops, that's not what I wanted to do. Let's see if this will do it. So two types, linear and cyclic. So a linear accelerator is just exactly what you would think it is. The particles move in a straight line path. Linear accelerators, they move in a straight line path. Cyclic accelerators, the particles move in some sort of curved path. Could be a circle, could be an ellipse, a variety of shapes are out there. These accelerators usually use magnetic fields to focus your charged particles. So the particle travels down a path and you have magnets on either side, strong magnets that compress the beam. And you can even, by adjusting them, tilt your beam right or left along the way. And then you can use an electric field to accelerate these particles to higher and higher energies. So one particular aspect of an accelerator might be to use a storage ring. A storage ring stores particles that have already been accelerated. So why would we want to do that? Well, it doesn't change the energy of the individual particles, but by increasing the number of particles, you increase the probability that a reaction will take place. So storage rings increase the probability of a reaction taking place because it increases the number of particles you'll then shoot down and at your target. You can also use colliding beams. And in this instance, what you do is you produce higher energies. So think about conservation of linear momentum. If you have a car sitting still and something slams into it, momentum is conserved and you get one result. If you have your same car slamming into another car and it's a head-on collision, if you have a head-on collision, what happens is that there's more net energy involved because both particles are moving. So with colliding beams, you have higher energies because there is no stationary target. So this is a diagram showing you a cyclic accelerator. So you have two circular paths, and then they'll come together and be shot at a target. So they'll go in a circular pattern until you're ready to send them off at their target. And then typically you'll notice that there are 3 paths down here exiting our circular accelerator. And the reason is that sometimes you'll have 3 different experiments set up at the same time. And so you can do one big setup and look at 3 different end results. So a linear accelerator, here you can see in our diagram, we have, this one has colliding beams. So you have the blue path on the right-hand side takes particles, and then on the left-hand side, you have additional particles, and they come together in a head-on collision right here. So this particular linear accelerator, the charged particles travel in a straight path. Looks like we're accelerating positrons and maybe electrons. So here's an electron. Yes, positrons on the left, electrons on the right. And the end result is that you have a collision that has greater energy because it's a head-on collision. So let's look at some of the beginnings of elementary particle physics. We used to think that atoms were indivisible, and then we learned about protons and neutrons and electrons, and we thought those were indivisible. And now we know that there are more than 300 particles that we classify in a group called elementary particles. What they've done is given us insight into the substructure of matter and into the origins of the universe, in fact. So these elementary particles play a particular role in talking about how the universe is started. What's really cool about particle physics is it takes relativity, quantum mechanics, electrodynamics, and gravitation and pulls it all together. So currently we have 4 fundamental forces. We have the strong nuclear force, the electromagnetic force that combines electric and magnetic forces, the weak nuclear force, and the gravitational force. And you can see if we make the strong nuclear force have a value of 1, everything else is weaker in comparison. The electromagnetic is a factor of 100 less. The weak nuclear is 1,000,000 less, and gravitational is way less than that. I don't know what 10 to the minus 38 is in words, except teeny tiny. So you can see that the strong nuclear force, because it's what holds the nucleus together, is a very short range force. Remember that a femtometer is 10 to the minus 15 meters. The electromagnetic is a long range force. Weak nuclear, again, because it's associated with the nucleus, is a short range force, and gravitational is again a long range force. And we have these field particles. So for the strong nuclear, the field particle is a gluon. For the electromagnetic, it's a photon. For the weak nuclear, it's bosons. We have 3 different types listed, W+, W-, and Z. And for gravitational forces, our field particle is the graviton. We'll talk about what we mean by a field particle in just a minute. So you can see we have a little graphic trying to remind you of what these 4 forces are involved with. So we have our little graphic. So the 2 short range forces are associated with our nucleus. In 1935, a Japanese physicist named Yukawa predicted the existence of a particle to mediate the strong nuclear force. So what do we mean by mediate? We assume that non-contact forces, that forces that don't require touching, but have to travel through space. Well, how do they get from one to the other? How do they exert? How does a magnet exert a force through empty space to pick up things? Well, they proposed it does it by exchanging a particle to mediate or to transfer the force back and forth. So maybe the best way to think of this in a standard example is to think of two kids on roller skates throwing a pillow back and forth. If one child throws a pillow at the other one and he catches it, the child that catches the pillow is going to roll because the pillow brought energy into the situation. So that's what we think about the forces that act at a distance. They have to have something that takes the role of the pillow to take the energy from one and move it to the other. So we say they mediate the force. So the strong force is mediated by the gluon. Gluons don't have any mass and they have a spin of 1. The electromagnetic force is mediated by photons. Photons, again, are massless and have a spin of 1. And then we've got the weak force. It's mediated by these bosons. They do have a mass. They do have spin. And they've been experimentally verified back in 1983 at CERN, which is an international research facility in Europe. So the gravitational force is mediated by the graviton. It should be massless. It should travel at the speed of light and have spin of 2 and interact with all particles. You'll notice when we talk about the graviton, we say should, because we actually have not discovered, we don't have physical evidence that a graviton exists. People periodically look for it, and so far they have not been successful. We know gravity is real. We know if you let something go, it falls. But we don't have experimental evidence for the mediating particle, for the field particle of the graviton. We do believe right now that the weak and the electromagnetic forces are just one force, and they've chosen to call that the electroweak. In time, this may change, or it may just be verified more strongly. So like I've said, we verified all of the field particles experimentally except for the graviton. It is the odd one. So most particles are assumed to have an antiparticle. We've actually talked about one of these. The first antiparticle discovered was the positron. Remember that when we talked about beta plus and beta minus emission, well, beta minus is just an electron and beta plus is just a positive electron. And so the beta minus and the beta plus are particle and antiparticle. Beta minus is the particle, beta plus is the antiparticle. Antiparticles have to have masses that are identical to their particle partners, but they have opposite charges. And then the real trick is that when you have a particle and its antiparticle and they meet each other, they're going to annihilate. So you'll end up with no particle, just a bunch of energy associated with this annihilation. So as we see in the little graphic, electrons are the particle and the antiparticle is the positron. If a proton is the particle, the antiparticle is the antiproton. If the neutrino is the particle, the antineutrino is its antiparticle. So particle interactions and conservation laws. Well, we know that the law of conservation of energy holds, the law of conservation of momentum holds, the law of conservation of angular momentum holds. And in fact, the law of conservation of electric charge holds. So we have experimental verification that these laws hold true. Elementary particle physics has shown us some new conservation laws, and we look at them to explain reactions that we can't explain any other way, or we look at them to explain reactions that seem improbable but exist. So we'll look at some unusual conservation laws in just a minute. So particle classification, we classify particles in one of two ways. We've got two systems. So just like at the university, I could divide students up into by major. I could divide students up by height, everybody 5'5" and under in one classification, everybody 5'5" and over in a different classification. I could divide them up by people getting Bachelor of Arts versus Bachelor of Science. I could divide them up by freshman, sophomore, junior, senior, or graduate student. So classification systems just allow us to group like things together and then study them based on the rules of our classification. So particles are the same way. We can divide them up into fermions and bosons. That's one classification. Or into gauge bosons, leptons, and hadrons, and that's the second classification. So let's look at these just for a second. We won't do a lot with them. If we look at fermions and bosons, so the pink circle are the fermions, the yellow circle are the bosons. You can see that fermions and bosons, well, mesons are fermions, gluons are fermions, photons are fermions, and so on. Bosons, that's leptons and quarks and baryons. So this is one way to look at things. Let's look at some of the classifications. So fermions have half integer spin. They have an asymmetric wave function, and they obey the Pauli exclusion principle. And some examples of things that fall into the classification of fermions are protons, neutrons, electrons, quarks, leptons, and so on. And then bosons have integer spin, and they have a symmetric wave function, and they do not obey the Pauli exclusion principle. So some examples of things that fall into the classification of bosons would be photons and gluons, the helium-4 atom, and so on. Now, the boson fermion classification is based primarily on the spin of the particle. So again, bosons have integer spin, fermions have half integer spin. So it's one quick way to separate things. If we look at our second classification, leptons, hadrons, and gauge bosons, so you've got all particles, and we divide them up into leptons. That would be electrons, positrons, muons, neutrinos, or bosons. That would be photons, the Higgs boson, the W and the Z boson. If we look at hadrons, hadrons are subdivided into baryons and mesons. So we have subparticles. Notice that baryons, well, that's where the protons and the neutrons fall under that classification. So it's just a way of grouping things depending on how you want to study them. So besides being classified as fermions or bosons by their spin, subatomic particles fall into, like I said, these three categories: leptons, hadrons, and gauge bosons. Leptons interact by way of the weak nuclear force and have spin 1/2. Hadrons interact by the strong nuclear force. They are the most, there are a large number of them, so we assume that they're probably really not elementary particles, but composites of something smaller. And in fact, now we think they're made up of quarks. We'll talk about those in just a minute. And we can subdivide hadrons into mesons and baryons. And then finally, under this classification, the gauge bosons are the messengers. So it would be the particles that mediate the electromagnetic and the weak nuclear forces. So let's talk about strange particles. I alluded to them earlier. I just didn't give them a name. So certain particles are always produced in pairs, and they decay at rates that are very unusual. To explain this process, they came up with a new quantum number called strangeness. So the law of conservation of strangeness says that strangeness is conserved in the by the strong nuclear force interactions, but not in weak nuclear force interactions. So it's only sometimes conserved. And in physics, when it's only sometimes conserved, we think of that as strange, and so that's where the name came from. So this is our first example of a partially conserved quantity. Remember before we said mass is conserved and charge is conserved and momentum is conserved. Well, strangeness is only partially conserved. And that brings us to quarks. So hadrons have an internal structure and they are made of quarks. They are made of quarks. So we believe that hadrons are made up of 3 quarks. The original 3 quarks were given names of up, down, and sideways. We've changed all that. Now we think that there are 6 different quarks. We call them up, down, strange, charmed, bottom, and top. Bottom and top used to be truth and beauty, and I don't know why they changed them, but they did. So up and down, strange, charmed, bottom, and top. I've often puzzled where these names came from. I think they were in a bar having a drink and they did it on the back of a napkin, but that may not be the case. So mesons are formed from a quark and an antiquark. Baryons are formed from 3 quarks. Oops. So while we search for new quarks, we ended up finding new properties or quantum numbers. So the quantum numbers for charm, bottomness, and topness have been added to the list of quantum numbers. We assume that strangeness, charm, bottomness, and topness are all conserved in the strong interaction, but not the weak. So to look at the standard model and quantum chromodynamics in the electroweak theory, we need to get back to quarks again. So we distinguish between the 6 quarks. Remember, that's up and down, strange, charmed, bottom and top, by saying that each has its own flavor. I know, it's weirder and weirder. So flavor is the name given to a property that makes one quark different from the next. It makes one quark different from the next. If we went back to our analogy of separating students, maybe we did it by, are you a freshman, a sophomore, a junior, or a senior? The flavor would be your earned credit hours, because that's how we divide things up. That's what makes a freshman different from a sophomore, different from a junior, different from a senior. It's not your age, it's the number of credits you've accumulated. So anyhow, back to quarks. So our 6 flavors are up and down, strange, charmed, bottom, and top. This helped, but there are some instances where quarks would not obey the Pauli exclusion principle. And so to force them to obey this, we created a new characteristic and we called it color. So now every quark can be one of 3 colors, red, blue, or green. And this should come as no surprise. Antiquarks come in anti-red, anti-blue, and anti-green. Baryons are made up of 3 quarks and one of each color. Well, guess what? If red, blue, and green visible light make white light, well, red, blue, and green quarks make white quarks. So we say baryons are white in color. And again, remember, it's not a physical representation. They're not really colored. It's just a way to categorize things. Mesons are made up of a quark and its antiquark, so they are colorless because blue and anti-blue would be colorless, just like red and anti-red would be colorless. Quarks are assumed to carry a color charge, which is similar to an electric charge, but different. The strong force between quarks is often called the color force. So this new theory of the strong force is called quantum chromodynamics, the chromo part standing for color, and because of the color charge and the colors on the quarks. Particles that transmit the color force are called gluons. They're called gluons. We've got 8 gluons. They're all massless, but 6 of them do have a color charge. An interesting aspect of our color force is that its strength increases with increasing distance. You think about that. Magnetic force decreases as you increase the distance. Electric force decreases as you increase the distance. Gravitational force decreases as you increase the distance. So common sense would say, gee, I bet all forces decrease with increasing distance, but we would be wrong because the color force goes up. So as quarks become closer and closer, the color force becomes weaker. This is sometimes described as asymptotic freedom. And here we have a little graphic showing you the proton with 3 different colored quarks, 2 ups and a down, an antiproton with an anti-up, an anti-up, and an anti-down in opposing colors, and so on as we go along. It's just a way to show you how they symbolize things. So scientists are continually trying to unify all of the forces under one single theory. To combine the weak and the electromagnetic, we came up with the electroweak. But if you want to combine all of them, if we combine QCD for the strong force and the electroweak, then we would have what's referred to as the standard model. But if we can combine those, then we would call it the grand unified theory, or GUT, G-U-T, for grand unified theory. The graphic sort of helps us understand why we might think that's possible. If you look at the strength of the force and the energy associated with it in GeVs, notice it's not MEVs, it's GeVs, a power of 1,000 more. So you've got the strong nuclear, the electromagnetic, and the weak, and they seem to all merge at high energies. And so that's why we assume that perhaps the theory can merge if we end up with a high enough energy. So in an attempt to include gravity and combine all the forces into a single theory, we would have what's called string theory. And in that theory, elementary particles are viewed as one-dimensional strings that are really short, rather than thinking of them as points. In the past, we would think of them as like little pinpoints, but not in string theory. An offshoot of string theory is superstring theory, and in which supersymmetric particles exist and may even form dark matter. So dark matter is the non-luminous matter in the universe. So we know it's there. We just can't see it. But we are investigating. So dark matter is a up-and-coming topic in physics. And this is all I'm going to say about particle physics. I know I've had a lot of little snippets. It's more in the sense of looking at vocabulary rather than anything else. And so we'll stop the share and stop the chapter.